Welcome to lesson 4.6, quadratic functions in general form. In general form, as we saw in the previous lesson, is y equals ax squared plus bx plus c. This is the form we've been working with so far. And so we've already seen a little bit of what we can do with it. Now we're going to build even more. So our first thing we need to do is just note some key principles about general form. There's certain characteristics that are easier to find, certain characteristics that we're going to have to do a little bit more work for. Let's run through them really quick. So interpreting general form, when a quadratic is in general form, the constant term c is the y-intercept. This is the same idea as b when we talk about linear equations in the form y equals mx plus b form. So you'll notice that this works because when we look at y equals ax squared plus bx plus c, and we apply our definition of the y-intercept, which means that the value of your x coordinate is 0. Then we plug 0 in for x. This whole term becomes 0 when we multiply by 0. This whole term becomes 0. So we're left with just our constant. And so that's how that piece comes together. Our next property that we need to remember is that if it's factorable, general form can be factored to figure out your x-intercepts. Get it into your two binomials and you'll be able to figure out your zeros, your x-intercepts, your roots from there. Point 3 is that you can actually figure out your axis of symmetry and therefore your x value of your vertex by finding the mean of the x-intercepts. Now the reason this works is because all parabolas are symmetrical, and so each x-intercept is equal distance from the vertex horizontally. So by using this equation here, we can figure out the x value of my vertex and also my axis of symmetry. And that's what point 4 is really pointing out. It's that axis of symmetry also tells us our x coordinate. So I gave that one away. Our fifth point says that our y value of the vertex can be determined by subbing in our x value for the vertex into our equation and then just solving for y. And that goes for any point. If you know your x value, you can solve for y. This is still the same for a vertex. It's just because it's a critical point. It's a point that we always look for on our parabola that we specifically highlight that you can do this. So the y value of our vertex can be figured out by substituting in our x value and solve for y. So let's give it a shot. Example 1. We're given an equation. It is in general form, and we are going to find the intercepts, the equation of the axis of symmetry, and the vertex. So the first thing we're going to look for is the y-intercept because it's the easiest one to spot. We don't have to do anything to the equation in order to be able to figure it out. So for A, I can tell you immediately that my y-intercept is at 10. My x-intercepts are going to be a little bit more tricky. I'm going to want to factor this trinomial. But that's actually not that bad either. It looks horrible because it's got decimals, but we can get rid of those. So we start with y equals negative 2.5x squared minus 7.5x plus 10. But 2.5 goes into all three of those values evenly, actually. And we want to take that negative away from our x squared term if we can. So I'm going to take out the full negative 2.5. 2.5 divided by 2.5 is 1, so that leaves me with x squared, positive because I've taken the negative with it. Negative divided by a negative is a positive, and 7.5 divided by 2.5 is actually 3, so I've got 3 x's now. And 10 divided by negative 2.5 is going to be negative 4. Now that's a more manageable factoring polynomial because it's got an a value of 1, which means it's a simple trinomial. Now remember, when we're talking about our x-intercept, y is equal to 0. So I'm going to set y equal to 0 here, and I'm going to factor from there. So I need two numbers that multiply to give me negative 4 and add to give me positive 3. So I'm going to go positive 4 and negative 1. I can divide this negative 2.5 away if I really want to, but I know it's a constant, so it's not going to be able to be set equal to 0. My only options are that x plus 4 could be equal to 0, or x minus 1 could be equal to 0. So those are the two that I deal with. X plus 4 equals 0, so x equals negative 4. Alternately, I've got x minus 1 equals 0, so x equals positive 1. And those are my two x-intercepts. So negative 4 and positive 1. So that's my answer for A. B is a little bit trickier. I need to find the mean of my two x-intercepts. Now, I could do this visually. I could set it up on a number line, have negative 4, negative 3, negative 2, negative 1, 0, and 1, and literally find the middle. 1, 2, 3, 4, 5, 6, and halfway there is going to be right here, which is negative 1.5. Or I can use the equation that we have above. So x equals x1 plus x2, all divided by 2. In this case, it would be negative 4 plus 1 divided by 2. Negative 4 plus 1 is negative 3, divided by 2 is negative a half. Negative a half, but negative 1.5 or negative 1.5. Either way, I get the same answer. This is my axis of symmetry. For part C, I need to identify my vertex. So I know my x value of my vertex because it is the same as the axis of symmetry. The axis of symmetry runs through my vertex. So I know my x value is negative 1.5. I just need to figure out my y value. I can do this by just simply plug and chug. I go back to my original equation. I'm going to convert these to fractions just because I prefer dealing with fractions if I can. And I do this because I like mental math, not because I actually like fractions. Let's just be clear on that. Okay, and from here, I solve. Negative 5 over 2 times 9/4 plus, it's going to be 15 times 3 is 45, okay, but it's positive times the negative, so I'm actually going to be subtracting, plus 10. It's going to be negative 45 over 8. So I'm going to turn everything into denominators of 8 as well. So it's going to be minus 90 over 8, and then plus 80 over 8. So that's just actually negative 10 over 8 instead. So that leaves me with minus 55 over 8. So we can leave it like that. You can convert it back to a decimal, whatever you want to do. But in the end, we're going to have some sort of funky number. So if our x value is a fraction or a decimal, odds are our y value is going to be as well. So I'm going to convert that to a decimal now, 55 divided by 8, and that is 6.875. Negative. If you go through and instead you didn't convert to a fraction, that's totally fine as well. You'll just be using your calculator throughout the whole process. This is my final answer. Example 2. Sketch the graph of the following quadratic function. Well, this particular one isn't actually factorable, and since we don't know how to deal with that just yet, we're learning in our next lesson, we're going to change this for now, and we're going to call it 16 instead, and this should work. We are not specifically asked to find the characteristics of our quadratic function, but we cannot put pen to paper and actually graph the function without knowing anything else about it. If we were using a graphing calculator and we were in applied, this would be a different story. We'd just plug and chug in our calculator because it could graph it for you. But we are not in applied, we are in pre-cal, and we do things a little differently. So we start by identifying our y-intercept, and that is at -14. Our x-intercepts are going to be at, well, we don't know yet, but we can factor and figure it out. Take the -2 out since it goes into everything evenly, and we're left with x squared minus 8x plus 7. From here, we can factor it a little bit more. If you want to divide by -2 to just get rid of it entirely, go right ahead. I'm going to keep it around just so that I don't have to do any unnecessary moving of things. From here, I need 2 numbers that multiply to give me +7 and add to give me -8. So it's going to be subtract 7 and subtract 1. So I have my 2 factors. Both of them could possibly be 0 based on the 0 property we learned about way back in 3.2. So we've got x minus 7 is 0. That would mean that x is +7. Or it could be that x minus 1 is 0, so then x would be +1. So I've got 2 answers again for my x-intercepts. There we go. So we're getting there. Now I need to know my axis of symmetry. So we do that by finding the median of our 2 x-intercepts. So the x for AOS is 1 plus 7 divided by 2, or 2x values divided by 2 to find the average of them. So that's 8 divided by 2 is 4. So my axis of symmetry is at x equals 4. This also means that my vertex is at x equals 4. Now I just need to figure out my y value. Plug and chug. -2 times 4 squared plus 16 times 4 minus 14. So -2 times 16 is -32. Plus 16 times 4 is 64 minus 14. So that takes me down 54, 50, down another 30 is 20. That leaves me with 18 as my y value. Okay. So I've got some pretty crazy stuff going on. This is a very stretched graph. We're going to need to watch out while we're plotting this. Go up by 2 on my horizontal, on my x-axis, because I don't have room for 7 here, I don't think. 1, 2, 3, 4, 5, 6. Oh, I do. Excellent. Let's go up by 1 then. And vertically, I'm going to go up by 2 because not only do I have to, actually I'm going to go up by 3 because not only do I have to fit -14 in here, but I also have to fit +18. So I'm going to go up by 3 and I'm going to go down by -3 on my y-axis. And here we go. Y-intercept at -14. So 3, 6, 9, 12, 14 is approximately there. Then I've got x-intercept at 1 and 7. From here, I've got my vertex at 4 and 18. 3, 6, 9, 12, 15, 18, 4. Now I have some critical points. Now it's just a matter of connecting my points in a parabola fashion. It's got to be symmetrical. That's the trick here. Got my point here for my vertex, and I'm gonna try and be symmetrical there too. Okay. So I don't expect your parabola to be absolutely perfect, but I do expect, again, that curve, not a V at the vertex. And I do expect it to look somewhat symmetrical, definitely hitting our critical points that we've already identified. And that's how we sketch a graph. Try again. So again, we start with our y-intercept because it's the easiest thing to identify in general form. X-intercepts need to be identified by factoring. So I set y equal to 0 because that's my definition of an x-intercept. And I'm factoring a complex trinomial. The reason it's complex is that 4 does not divide into, I shouldn't talk while I'm writing, 4 does not divide evenly into both 12 and 5, which causes all sorts of problems. So instead I'm going to factor it. Again, you can use the crisscross method if you want. I really like the unfoiling method. I know a number of people also have started using the grid method, where we are like, okay, well maybe it's 2x and 2x, that gives us 4x squared. Maybe it's 5 and 1, or other pieces, so that's 10x and 2x. Well, if we look at that, that gives us our 12x, so that works. And then 1 times 5 is positive 5. So we can use this method also. That's option number 3. And then we know that this part here and this part here form my two pieces. So I've got 0 equals 2x plus 5 and 2x plus 1. This means that one of my two factors is equal to 0 because when they multiply they equal 0. 0 property again. So 2x plus 5 equals 0. So x equals negative 5 halves. Or it could be that 2x plus 1 equals 0, in which case x equals just negative 1 half. So those are my two possibilities. Again, you could convert these to decimals, but in terms of mental math and the ability to do it without a calculator, which is our goal, to never rely on our calculators if we don't have to, then we will leave them in fraction form, because that makes it a little bit easier to identify my axis of symmetry. How do I do this? Again, I'm going to calculate it. I'm just going to use purple here so I don't get confused. I'm going to use that equation. Find the average of my intercepts. So it's negative 5 halves plus negative a half, or subtract a half, all divided by 2. If we combine these, we get negative 6 halves. And when we talk about dividing by 2, that's the same thing as multiplying by a half. Or you know what, before I even do that, negative 6 halves over 2. Well, this is the same thing as negative 3. So it's going to leave me with negative 3 halves. And so that is my axis of symmetry. What do we do once we have that? We figure out our y value for our vertex so we can identify our vertex point. So it's at negative 3 halves and something. So I use my equation again. 4x squared plus 12x plus 5. I'm going to plug in my equation. 4 times negative 3 halves squared plus 12 times negative 3 halves plus 5. This fraction squared is going to give me 9/4. When I have a 4 in the numerator and the denominator, 4 divided by 4 is 1, so those cancel out. We also have 12, and 2 goes into 12 evenly, so we can say that that's 6 instead. 6 times negative 3 means I'm not adding, but subtracting 18 and adding 5. So I've got 9 minus 18 plus 5, or 14 minus 18, which is negative 4. So unlike the previous question where I said, or 2 questions ago when I said, if we got a wonky x, we'll get a wonky y, not always the case. So we've got a pretty nice whole number for our y value for a vertex here. Again, using these characteristics, I'm going to scroll up just a little bit so I can see them all at once. Using all of these guys here, I'm going to plot my points. My y-intercept and vertex are much more manageable here, so I'm going to just go up by 1 and down by 1 on my y-axis. Because my x-intercepts are all fractions, I'm actually going to go up by half. So instead of labeling a half in here and labeling fractions, because that can get pretty messy on my graph, I'm just going to identify that this skipping over 1 is going to be -1, and skipping over 1 over here is going to be +1. Now it's just a matter of plotting our points. So my y-intercept is at +5. 1, 2, 3, 4, 5. And I have to name this axis. My x-intercepts are at -5 halves and -1/2. So -1/2 is easy enough to find. -5 halves, so that's 1, 2, 3, 4, 5 halves. Alternately, you could have figured out that that's the same thing as 2.5 and gone to that value as well, whichever way you want to think about it. And then we know that our vertex is at -3 halves, exactly halfway between them, or -1.5 if you want to think about it that way, and at -4. Once again, now that I have all these critical points identified, it's just a matter of connecting them. And I want to stay true to that parabola shape. So I'm going to curve this way. I'm going to curve this way, and I'm going to even make sure that I hit that symmetrical point there to match my y-intercept. And now I've got my beautiful parabola. I'm even going to label my function y equals 4x squared plus 12x plus 5. And I forgot to do that on the previous one, so I'm going to go back now and do that as well. And that's how we go about graphing in general form. We have to identify these characteristics in order to be able to put our function in graph form. Okay, so this question's a little bit different because we're not actually asked to graph anything. Instead, we're asked to write the equation. So we're going to have to use some different principles than we already had. First thing we're going to need to do is we're going to go through the question and identify the information and how we're going to use it. So we're told it's a quadratic function, and it passes through some point. We don't know what that point is, but it's there somewhere on our graph. And we are told the zeros of our function are at these two values. Now remember that zeros are referring to our x-intercepts. We call them zeros because our y value at that particular point is equal to 0. Well, we do know that when we factor our equation, we should be able to actually figure out our zeros. So we should be able to work backwards hypothetically from there. So we'll start with the idea that x plus 4 and x minus 2 are our two factors. And those have to be true because our whole graph is kind of based on it. Our roots have to be there. This also works because once we get to positive 6, we're going to be way down here at negative 60. That's going to be point C. Again, this is just a sketch for me to kind of wrap my head around what's going on. It is not actually for the purpose of this question because we are not asked to graph anything. And it is definitely not to scale. So this is great, except for the fact that we've got 6 and negative 60. Now our parent function, when we dealt with just y equals x squared, it did not increase that fast. If you remember what our table of values looked like, it was like negative 3 and 9, negative 2 and 4, negative 1 and not 0, but 1. So it's not changing very fast. But here, in a matter of 4 values, we go all the way from 0 to negative 60. So that's huge. So that is not enough. We can't just say y equals this and we're done. That is not good enough. We need to account for that point. And how we're going to do that is we're going to say we're going to multiply. So we're missing that a value. We must have had some value out in front that's stretching our graph so that it changes super quickly to the point where we're getting to negative 60. So let's check and see what it is. We do this by plugging in our points. So this is our x value and this is our y value for that particular point. Those are our coordinates. So I'm going to put them in my equation. So all of a sudden, I can enter negative 60 for my y value. A becomes my new variable that I don't know yet. And x is actually going to be 6. Again, the talking with the writing thing is not working right now. So now I've plugged in these values. My x's have been substituted with 6 and my y is substituted with negative 60. Well, I can work with this. I can turn this around and isolate a to figure out what my variable was out in front. How do I do that? BEDMAS. So I've got negative 60 stays over on the left. A is still here. Inside my brackets is the first thing we need to do. I look and I say, okay, I can simplify that. 6 plus 4 is 10. My second set of brackets, I can simplify that too. 6 minus 2 is 4. Okay, so I can actually simplify that even before I start moving things around. So it's a times 40. Again, I want to isolate a. I want to figure out what the heck was I multiplying by to get this graph to change so fast. So I divide by 40 to get a by itself. For a is equal to negative 60 over 40. We can reduce that by dividing by taking out a 10 from each. 6 and 4 still have a 2 in common, and so that's going to leave me with negative 3/2. That's my a value. Which means now, if I take those two pieces, I can rewrite this equation, and I can be almost 100% certain that I am right, assuming that I didn't make any arithmetic errors. We all know those happen. But is this the answer to the question? If we go back to our question, it is asking for the equation. Sure, we've got an equation, but we do not yet have it in general form. So we need to get this together. How do we do that? The reverse of factoring, we distribute, which could result in you thinking of FOIL, firsts, outsides, insides, lasts. So we go firsts, outsides, insides, and lasts results in FOIL. So we multiply that. 3 halves can hang out in front for now. We want to deal with fractions as late as possible in the game, as usual. X squared, got minus 2x plus 4x minus 8, which is the same as x squared plus 2x minus 8. We're going to multiply by that value out in front, so we've got negative 3 halves x squared minus 3 halves times 2. The 2's will cancel each other out, so it's going to be just minus 3x. Negative times a negative is a positive. 3 times 8 is 24 divided by 2, 12. And so that, with y equals at the front, is my general form, and that is my final answer. So stopping here with it in factored form is not good enough. You need to expand and have it as those 3 distinct terms: the term with a degree of 2, term with degree of 1, and a constant. So that's the last example for this lesson. There's lots of practice questions for you to do. Start in your work text, and then if you're feeling extremely confident and wanting to challenge yourself, do the practice questions following this in your booklet.